Okay, let's start. In this lecture, we will talk about the introduction of the linear transformation. Okay, so here's the motivation. Okay, until last lecture, we were talking about the two forms of the linear system. The first one is the Ax equals b, the matrix equation form, and x times column vector a1 plus the x n times column vector an is equals b. It is the vector equation, right? So these two cases have the exactly same meaning, right? Uh, they are just the matter of the notation, right? But in a matrix equation Ax equals b, we can think of the matrix A as an object that acts on the vector x by multiplication to produce the new vector Ax. What does it mean? What does it mean? So in the Ax equals b form, we can think of this matrix A as a transformer or some object that act on the vector x. Okay, so this is the concept of the linear transformation. Okay, here's the example. Okay, so here is some kind of vector matrix A like this, and there is the vector x, and there is a vector let's say b, right? So this is the general formulation of the Ax equals b, right? Actually, it was the non-homogeneous case, right? Then what is the homogeneous case of this linear system? Here is a matrix A, and here is a matrix vector x with some zero vector, right? So in other words, this is the Ax left side is meaning that the Ax equals b, and right hand side means that Ax equals 0. So non-homogeneous system and homogeneous system. Then what's the meaning of the linear transformation in this case? The linear transformation is the mapping a vector by a matrix is the linear transformation. What does it mean? Mapping a vector, this vector x, by a matrix A. So this A times x means the linear transformation. So here is the figure. So okay, let's say here is the R4 space, right? And there is some vector x here. In this case, 1 times 1, 1, 1, 1, right? Then what is the A times x? A times x will make some vector b. Okay, let's say 1, 1, 1, 1, right? In this case, the mapping vector x by the matrix A is the vector 5, 8, like this, because this is the A times x, right? So what is the size of this vector? R2, right? R2 space. So this vector x will be transformed to the vector b. Then what about the vector u? What about vector u? Okay, in this case, okay, let's say this is vector u, okay? So in this case, vector u can be transformed to the 0 here, right? But it's still in the R2 space, right? So in this case, the multiplication by A is called the linear transformation. Okay, so this is the concept of the linear transformation. Why we need a linear transformation? Actually, we already learned what is ax equal b and why ax equal 0 or why au is equal to 0, something like that. But by introducing the linear concept of the linear transformation, we can think of the matrix multiplication as some kind of transformation. Okay, so formally the transformation, which is called the function or the mapping, like that. Let's say the t from the Rn space to the Rm space. In this case, we transform the some vector in R4 space to the R2 space. So generally, we can say that some kind of transformation or the function or the mapping from the Rn to Rm is a rule assign a vector x, each vector x in Rn space to a vector Tx in the Rm space. Okay, so in this case, the space Rn, the input space, is called the domain of the function or transformation, and this Rm space called this is output space, right? The Rm space called the codomain of the transformation T. So today we will use the notion of the domain and the codomain. Okay. So we can represent the transformation T as a Rn to Rm, like this, that indicate that the domain of T is Rn and the codomain of this transformation is Rm. Okay. So in this case, this is the domain. This is the codomain. Right? So this is the definition of the linear transformation. Then, yeah, here is another figure. Okay, let's say for vector x in Rn space, like this arbitrary vector here. Rn space, the input space means the domain, right? Then the vector tu, the transformed by transformer t here is called the image of vector x. Image of vector x. So this point called the image of vector x. Okay. Then each vector in the domain can be mapped to some space in the Rm, right? Then those every values can make some plane in the Rm space. Then so set of the all images here is called the range of T. So the range means the whole possible output vector from the input vector. Okay, so this is called the range. So in this case, this Rm space means called the codomain. Okay, so this is the definition of the linear transformation. To summarize, so the linear transformation is find the mapping function between domain to the codomain. Then each vector x will be projected to the image of the vector x here. Then and whole images from the input or the domain is called the range or in the codomain. Okay, so this is the definition of the linear transformation. we can extend this linear transformation concept to the matrix transformation. Actually, this matrix transformation is exactly the same as a linear transformation. Okay, let's say the vector x in the Rn space. The transformation Tx, transformation this T or Tx can be computed as a Ax. We are still interested in the Ax, right? So to solve the Ax equals B or the Ax equals 0, right? Then anyway, so A, as usual, A is the n by n matrix. Okay? So we can represent the matrix transformation something like the A times X. Okay. For simplicity, we denote such a matrix transformation by A times X, something like that. Then in this case, so what is the domain of this matrix transformation? Rn, right? Then what is the codomain of the matrix transformation? Rm. Why? Okay, let's redraw the A times X. Okay, let's say there is a matrix A whose size was the m times n, then vector X the size was the n times 1. Let's use the different color, m, n, n, n. Okay, so what is the rule of this matrix A? This matrix A transform this input vector to the some kind of the output vector B, whose size is m times 1, right? So it means that this will be the domain, this will be the codomain. Then domain of this matrix transformation is the Rn space, right? Here. And codomain of this matrix transformation Rn space from here. Okay? So this is the domain and codomain in the matrix transformation. Then what is the range of this transformation? The range of transformation is what is the range of transformation? Output of the whole possible what? Input. Like this, right? So what does that mean? From here, as bearing this vector x, we can generate so many output, right? Then what is that? This is some kind of the linear combination. There should be, yeah, x, a, n, something like that. So in this case, the output of the whole possible input is the set of the all linear combination of the columns of A, right? What does it mean? This is the span of the A1, A2 through the AN, right? So the range of the matrix transformation is the linear combination of the columns vectors of A or the span of the column vectors. Okay, so this is the domain, codomain, and range in the matrix transformation. Okay, let's see the example. Let's say matrix A is equal to something like this, and there is some kinds of the vector U, vector B, and the vector C, something like that. First of all, let's define the transformation T R2 from R2 to R3 by the matrix transformation AX or A times X. Then, first of all, we can represent this transformation T over X as A times X. Then, what was the A? A is here, right? Then, we don't know the X vector X yet, so let's say X1, X2, something like that. Then, how can we compute the matrix by vector? This first entry should be dot product of the first row with the vector x, right? What about the second one? The second row second row times this vector, right? What about the third one? Something like that. Yeah. So we can represent AX like this, right? So in this case, there are four kinds of the question. The first one, find the TU, the image of the U under the transformation T. Okay, so if we already know the vector U, then we can find the TU or the AU. AU was the image of the U. Then second question was the let's find the vector X whose image under T is B. Okay, so this is the second question. The third question is is there more than the one X whose image under T is B? This is third question. The final question was the determine if C is in the range of the transformation T. Okay, so there are four kinds of questions. Okay, let's solve the each question. First of all, the first question. Let's find the AU. Okay, this was the A. This is a vector U. Then how can we compute this? This row vector times this column vector, right? So it means that 1 times 2 plus -3 times -1. So in this case, 2, 3, it should be 5, right? What about this? This times this. Then this one, this row vector times the column vector, something like that. So this is the AU, or this is also called the image or vector U, right? This one under the transformation T. Okay, so the second question was solve the AX equals B, right? AX equals B. Because we already know the vector B and we have the vector A. Then how can we solve this? Okay, let's say this is the equation 1. How can I solve this? First of all, we have to find the augmented matrix of this system and then reduce those system into the echelon form or the reduced echelon form, right? So, okay, first of all, this is the augmented matrix of this system, right? Then what should we do? We have to remove this part, right? Then how can we do that? By using this row remove this row and this row. Remove this one. How? Let's say R1, R2, and R3. Then, first of all, R2 can be replaced by R2, original R2 minus 3 times R1. What about the R3? R3 will be replaced by R3 plus R1, something like that. Then this value will be 0, 0, and this is another term, right? Then what is the next step? We have to do the similar things on this sum matrix and remove this one, right? So finally we can make this echelon form of the matrix, right? Then to get the solution, we will do the further step to get this reduced echelon form. Okay? From this reduced echelon form, we can find the solution of the x1 is equal to 1.5, x2 is equal to negative 0.5. So finally the solution x should be something like this. So the question was to find the x whose image under T is P is this one, right? So the image of this x under this matrix equation, the vector B. Okay, so this is the second question. What is the question C? Third question. Is there more than the one x whose image is under T is B? What is that? What is that? Actually, this question is related to the second question, right? Why? Okay, let's say AX times B. Then this question is exactly the same, that there existed more than one solution that satisfy this relationship AX equals B. This question is related to the uniqueness solution or the uniqueness problem. Okay. So let's say this is the equation 2. From the equation 2, it is clear that there is the unique solution. What does it mean? Because there is no pre-variable, right? There is no pre-variable, so there is exactly one solution, right? So in this case, there is the unique solution. So this question was related to the uniqueness problem. So is vector B the image of the unique X in the Rn space? So this is related to the uniqueness problem. Okay, what was the final question? Determine if the vector C is in the range of the transformation T. What was that? Let's say AX equals C. The question means if there is the solution that's satisfying this one, right? So this question is related to the existence. So how can we solve this? The vector C is in the range of T if the C is the image of some vector X in the R2 space. That is, C is equal to TX or the AX. So this is another way of asking if the system AX equals C is the consistence or not, or existence or not, right? Then how can we answer that? We have to try to find a solution, right? So, okay, so AX equals C, right? What was the A here? Yeah, A was the 1, -3, 3, 5, -1, 7, right? Then X was the X1, X2, like that, and C, vector C, was the 3 to 5, 3 to 5, 3 to 5, right? So this is the system that we want to solve. So first of all, we have to find the augmented matrix of this system. So augmented matrix looks like this. Then what we want to do is to low reduce this original matrix into the echelon form or the reduced echelon form. In this case, this is echelon form, right? How? First of all, let's remove this part and remove this part here. It's like that. So finally we get the echelon form of the original matrix. What can we know from this echelon form? In the third equation, there is the equation something like that, or x times 0 times x1 plus 0 times x2 is equal to -35. So is there any solution that satisfies this equation? No, right? So any vector x cannot satisfy this one, right? So we can conclude that this system is inconsistent, or this system doesn't have any solution. So we can say that the vector C is not in the range of T. Like, where is that? It was the last one. Yeah, like this. The final, let's say this is the C and this is the column vectors of the matrix A. Then in this case there is no solution, right? So yeah, this question was related to the existence problem. Does there exist an X whose image is C? The answer was the no, right? So this is the example. Okay. It is the matrix transformation. Okay, let's see the examples of the matrix equation. There is very interesting example, shear transformation. Shear transformation is one of the popular matrix transformation. Okay, let's say matrix A is 1, 3, 0, 3, 0, 1. Then this transformation T is to find the mapping function from the R2 to R2, right? So we can represent this transformation is A times X, right? Then it is called the shear transformation. So what is that? Okay, we have a domain here in the R2 space. Then by using this transformation, let's say AX equal how can I represent? Yeah, like this, TX times AX, something like that. Then in this case 0 by 0, yeah, let's say 1, 3, 0, 1, x1, x2. In this case 0 by 0 can be mapped to this point, right? Then what about the 2 times 2, 2 comma 2? Let's say 1, 3, 0, 1, 2 comma 2 will be the 8 comma 2, something like that. What about this one? 1, 3, 0, 1, 2, 0 case. Then it will be the 2, 0, 2, 0, something like that. So it turns out if the transformation T act on each point in the 2 2 by 2 square, something like this. Then the set of the images or the set of the output form the shaded parallelograms, something like that. So to understand this, if we think about the shape of the ship, something like this, by applying the transformation A, we can get this shared shape, something like this. So this is the examples of the shear transformation. So in this case, this is the codomain, right? Actually, the linear transformation or the matrix transformation is the very popular or the very fundamental concept in the deep learning. If you remember our first lecture, I said that this linear algebra can be the fundamental technique in the deep learning or the artificial intelligence, right? So here is the example. Here is a very popular artificial intelligence network called the Spatial Transform Network. So from this image, something like that, we want to find this transformation field to estimate our final goal. In this case, the number recognition artificial intelligence system, right? Something like that. In this case, there was a very popular network called the Spatial Transformation. Actually, this Spatial Transform network was published in the New Leaves or the NIPS in 2015. Actually, this NIPS conference is one of the popular artificial intelligence conference in the world. So in the Spatial Transform network, there is some kind of vector matrix A with a vector rotation X, something like that, to get the new mapping position, something like that. So by using this transformation, we can transform the original features. Looks like this. So by using this one, we can solve the spatial deformation problem in the world. So if you are interested in this one, I made some seminar called the modeling spatial transformation using the deep convolution neural network. So there is a video link. Actually, it is the targeted to the graduate student who are working in the deep learning stuff, but as a freshman, you can also watch this video and can try to understand what's the meaning of the spatial transformation and what's the meaning of the deep learning. So yeah, if you are interested in, please try to watch this video. Of course, it's not mandatory, so you don't have to worry about that. Anyway, so linear transformation is also very important topic in the deep learning stuff. Okay, so it was a shear transformation. Then yeah, here is some transformation example, something like that. Yeah, this is a shear transformation. Okay, finally there are some property of the linear transformation. The linear transformation or the mapping T is a linear if the vector u plus v, in other words, the transformation of the vector u plus v is equal to transformation of the vector u plus transformation of the vector v. The second one is the transformation of the c times vector u is equal to c times transformation vector u. In the previous lecture, we introduced some property of the vectorization in the matrix equation, right? So this property in the linear system or the linear transformation almost the same to the matrix property. So in other words, this property of the linear transformation preserve the operation of the vector addition or the scalar multiplication. For example, yeah. How can I prove this one? How can I prove? How can we prove? Please remember, TU was the AU, right? Then, what was the left hand side of the first property? U plus V. Then we can derive this one, right? From the property of matrix. Okay. Then what is that? The transformation of the vector U. And what is that? Transformation vector V, something like that. So because this is the right hand side of this equation, so this is the proof of the first property. Okay. How can I prove the second property? Okay, let's write this left hand side as a C times a U, like that. Then it will be C U times vector U, and it will be the C U times something like that. So this is also the proof of this linear transformation. Okay. So actually, this is very easy because it is similar to the matrix property, right? Here are one more concept or one more property. If the transformation T is the linear transformation, then transformation of the zero vector is going to be 0. Then transformation of the CU plus DV is equal to C times TU plus D times the transformation V for all vector UV in the domain of T and whole scalar C times D. Yeah, what does it mean? Okay, because the Tx was the Ax, right? Then we can represent the Ax as in this case, A vector 0. It should be 0, right? It's easy, right? What about this? It can be easily proved by using these two properties, right? So you can prove this one by yourself, okay? And the linear transformation satisfy the four means this one. Then it must be a linear. So in other words, we can represent this property as a generalized form, something like that, using the more coefficient with the more vector, something like that. So in engineering and the physics field, it is often referred to as the superposition principle. So superposition principle is the really important concept when dealing with the linear system. Okay, so in other words, this vector V1 through the Vp as a signal that go into the system, and transformation of vector V1 through the transformation of the vector Vp as a response of the system of the signal. So What does it mean? Okay. Let's say we have some kinds of system. We don't know what it is. But this system has an input as a vector x and the output of the vector y. For example, it will be the vector matrix equation, something like that, right? Matrix transformation, something like that. Then what is this superposition principle? Okay, let's use the different color. What does that mean? Okay, there is the input V1 through the VP, something like that. Then output of this transformation will be the TV1, TV2 plus TVP, right? Right. So in this case, if we make a new input, thing like the C1V1 plus C2V2, something like the CPVP, right? Let's say this is the new input. Let's say let's say just V, right? So in this case, the output of this input V will be the some vector transformation of the vector V, like that here. So in this case, if the system is linear, this system is linear, the output of this one should be exactly same with the C1 times this one, V1 plus C2 times the transformation V2 plus CP times transformation V2P. Okay. So this is the very important concept of the superposition principle. Okay. So to summarize, if the system is the linear system, this kind of the relationship are satisfying. Okay. Okay. There are some statements. So the system satisfies the superposition principle if whenever an input is expressed as a linear combination of such a signal, then system response is the same linear combination of the response to an individual signal. Here, something like this. Okay. Here is the last concept. Given a scalar value R and define the transformation T by Tx is equal to R times vector X. In this case, this is very simple linear transformation or the matrix transformation in case of 1x1 matrix, right? So in this case, this transformation is called the contraction. When R is larger than 0 and less than 1, and dilation if the R is larger than 1. So this is a special case of the matrix transformation. Okay, this is the end of today's lecture.